Good morning everyone, my name is Ruchavinada and I'm from the class of DTK2D and my registration number is 01DTK24F1066 and today's topic I'm going to do is topic 3 and I hope you all enjoy the video. Okay, so now I'm going to talk about bipolar junction transistors, which is called BJT. The BJT is a fundamental semiconductor device widely used in amplification, switching, and signal processing. It consists of 3 terminals: base, collector, and emitter. And it operates based on the interaction of charge carriers, electrons and holes across its junctions. Basically like the human body. You can compare with these things with the human body, not as much but a little bit. Moving on to the objectives is that to sketch the BJT symbol and identify its terminals. The second objective is to use a multimeter to determine these terminals. To also determine the transistor's electrode and to check if it's NPN or PNP. And the third one is to check if it's made out of silicon or germanium, which I will explain after this. And for the third objective is to recognize the BJT terminals from their physical shape. The BJT terminals and functions. I'll tell you about the functions of the BJT. The BJT includes 3 things, which I already mentioned: a base, collector, and emitter. Starting from the base, the base controls the current flow between the collector and emitter. Simply as said, it controls everything. For the collector, it collects charge. It's pretty easy to understand. It collects charge carriers using electrons in NPN. For PNP, it's holes. For the emitter, it emits charge carriers into the base. Pretty simple, it's not that hard. For the current flow in NPN versus PNP transistors, basically we are comparing 2 things, NPN and PNP, between each other. For the NPN, the transistor for NPN, is that the current flows from collector to emitter when the base is forward biased, and the electrons are majority carriers. Compare this with PNP, current flows from emitter to collector instead of collector to emitter when the base is reverse biased. The holes are majority carriers. It's simply as that the NPN, it starts from the collector to the emitter, but when the base is a forward bias. When the PNP transistor, it goes from collector to emitter to collector when the base is a reverse bias. Moving on, the NPN requires a positive base emitter voltage. Meanwhile, PNP requires a negative base emitter voltage. So we can start off with the identifying the base, and the transistor we're about to use is this one. This is a BD135. If you can see it well enough, it says here 135. It's really hard to focus it, but I can promise you it says BD135 on it. So we're gonna find the base for this, and the first thing we gotta do is use a breadboard. We're gonna stick it in here. We're gonna plug it in here, and once it's fully in, like so, it's a bit like so, we can start off with our multimeter right here. So we have to plug these probes in the opposite sides. For the black one, we gotta go to the positive, while the red one, we gotta go for the negative. After we've done this, we need to calibrate these right here. So we already have it on 10 ohms, so we can stick it together and we can check if it's fully calibrated. As you can tell, it's really not that calibrated right now, so we can switch it up by tilting this dial until 0. There we go. Now it's fully calibrated, you can tell. So basically, you gotta put the positive on the first leg, the negative on the third leg. This basically means the multimeter has moved, as you can tell right there. So the first leg is now the base. We have found the base, so we can move on to finding the emitter and the collector. So the first one is the base for this transistor. The second one is a collector, while the third is an emitter. Since we're going to find the transistor, there's 2 types of transistors, which there is PNP and NPN. For this transistor right now, we're about to find out if it is the either. So we can take the positive. We take the positive, we put in the middle, and the negative we put on the third leg right here. As you can see, it has a reaction on the multimeter. So if we switch these two up right here, we put the negative on the first leg and the positive on the third leg, we have no reaction. So this basically means that this is a NPN transistor. Okay, so we can now start off to identify or find out what this little transistor right here is made out of. It's either silicon or germanium, which I have explained in these previous parts. So we have to put a red one, which is our negative, to the first part right here, the positive right here. As you can tell, we have nothing. We got nothing from our reading right here. There we go. Check that again. Boom, there's nothing. So from the base to the emitter, there's nothing going on. So if we move the negative to the collector instead of the base, there's also nothing. So this basically means this is made out of silicon, and this transistor BD135 is silicon. Now I'll be comparing between silicon and germanium. We're starting off with the property is that silicon is mentioned as Si in the table, the element table. For germanium, they call it Ge. It's very simple. And for the band gap for between two of these, that silicon has a 1.1 eV, meanwhile germanium have 0.67 eV. The thermal stability for silicon is high, up to 150 Celsius. Meanwhile, germanium can only go to low due to leakage. It is very easy for it to melt and leak. For silicon, the breakdown voltage for silicon is higher, meanwhile germanium is lower. The common usage for silicon is to modern circuits, meanwhile germanium is for old applications, very old. People prefer silicon, and this is because it has a higher thermal stability compared to germanium, and it has a better performance in high power applications, because the world nowadays needs better performing things in extreme conditions. Next thing is lower leakage current. This is because it can go, the breakage voltage is higher. It is more efficient, like I said, efficient switching. It switches in between. It has a wider availability and cost effective. It's not as expensive as germanium. Silicon is very easy to get, or should I say very easy to afford, and people would rather use silicon over germanium. With the key findings that I did, the base was identified using a multimeter continuity test. For the collector and emitter were distinguished based on resistance readings, which I already did, I showed you. The transistor type between NPN and PNP was determined by the polarity of the multimeter probe when testing the base, which I already showed in the video. The material SiGe, which is silicon and germanium, silicon transistors showed high resistance in both directions, while germanium transistors exhibited asymmetry. For the importance of these circuit designs, the amplification BJTs are crucial in audio amplifiers and signal processing. Meanwhile, for switching, it's used in digital logic circuits and power control. The material choice, silicon's reliability makes it ideal for modern electronics, while germanium is limited to niche applications, which I have explained this in the previous part, if you guys went back. Germanium is becoming old, is mainly used for very old applications back in the day, because silicon wasn't really up in the game. So right now silicon is the best choice that we have currently. And if you go back to the point, understanding BJT terminals, types and materials is essential for designing efficient and reliable electronic circuits, from simple amplifier to complex computer systems. And I think that would be all for my conclusion.